Welcome to the lesson on section 6.2, volumes of solids formed by revolving a curve about a non-axis line. In this lesson, you'll learn how to calculate the volume of a solid with a hole inside of it using the washer method, and how to use integrals to calculate the volume of a solid formed by a line parallel to the x or y axis. The example numbers in this series of videos will pick up where our class examples left off. In example 3, we need to find the volume of the solid obtained by rotating the region enclosed by the line y equals x and the curve y equals x minus 1 cubed plus 1 from x equals 0 to x equals 2 about the x-axis. Two different views of this solid are shown at right. In the smaller diagram, the solid formed by revolving the line is shown in blue, and the solid formed by revolving the cubic is shown in red. Those colors are reversed in the larger diagram. The examples you saw in class all formed slices in the shape of solid discs. This solid will form discs with holes in the middle, or washers. If you're unfamiliar with a washer, here's a picture of one. To find the area of the face of this shape, we would subtract the area of the outer circle minus the area of the inner circle. Pi times outer radius squared minus pi times inner radius squared. Factoring pi from this expression, we get pi times outer radius squared minus inner radius squared. It's important to notice that each radius is squared separately here. Looking at the two-dimensional graph of the line and the curve together, you can see that the curve that forms the outer or inner radii changes depending on which side of the intersection point 1, 1 we look at. So we'll need two integrals to describe this volume. In the region on the left, the curve forms the outer radius, and the line forms the inner radius. Volume for that region will equal pi times the integral from x equals 0 to x equals 1 of our outer radius squared, which is the cubic, minus the inner radius squared. The region from x equals 1 to x equals 2 will be similar, except that the line forms the outer radius and the curve forms the inner radius here. In example 4, we'll find the volume obtained by rotating the region between the parabola y equals 4 minus x squared and the vertical lines x equals 0 and x equals 1 about the line y equals 5. The solid is shown at right. I usually like to draw and label a sample slice for myself. You can see that the center of each slice is on the line y equals 5, and the bottom of each slice will hit the parabola y equals 4 minus x squared. The slices will be solid, so these are discs instead of washers. I can see that the thickness of each slice is horizontal, so I'll be using dx. The radius of this slice hits y equals 5 at the top, and y equals 4 minus x squared at the bottom. My integral will use pi times radius squared to calculate the area of the face of each slice. So we have pi times the integral from x equals 0 to x equals 1 of 5 minus 4 minus x squared squared. Notice here the radii are not individually squared. It's one solid radius. Now let's find the volume of the solid formed by rotating the same region about the line x equals 0. Since we always slice across the axis of rotation, our slices will look like this, and their thicknesses run vertically and can be described by dy. The radius is found by subtracting what x equals on the right minus what x equals on the left. Here our radius will be the square root of 4 minus y. This comes from isolating x in the equation of the parabola y equals 4 minus x squared. If the area of a face of the slice is pi times radius squared, our volume will be pi times the integral from x equals 3 to x equals 4 of the square root of 4 minus y squared dy. In example 5, let's consider the region between the graphs of y equals x to the 4th and y equals x to the 1/4. First, we'll revolve this region about the x-axis. A sample slice shows that we're dealing with a washer with horizontal thickness dx. So the area of the face of a slice will be found by pi times outer radius squared minus pi times inner radius squared, where the outer radius is y equals x to the 1/4, and the inner radius is y equals x to the 4th. The volume is pi times the integral from x equals 0 to x equals 1, where the two graphs intersect, of x to the 1/4 squared minus x to the 4th squared dx. Revolving the same region about the vertical line x equals -1, we slice across the line x equals -1. Slices will be washers with x equals -1 at the center. These slices have vertical thickness, so we'll set this up using dy. The outer radius, expressed as what x equals on the right minus what x equals on the left, hits the curve y equals x to the 4th, or x equals y to the 1/4 on the right, and the line x equals -1 on the left. This makes the outer radius y to the 1/4 minus -1, or y to the 1/4 plus 1. Likewise, the inner radius is y to the 4th plus 1. That makes the volume pi times the integral from y equals 0 to y equals 1 of y to the 1/4 plus 1 squared minus y to the 4th plus 1 squared dy. Lastly, let's revolve that region about the horizontal line y equals -1. Slicing across that horizontal line gives us washers with horizontal thickness dx. Using what y equals at the top minus what y equals at the bottom to calculate the outer radius, we get x to the 1/4 minus -1. The inner radius is x to the 4th minus -1. Then the volume is pi times the integral from x equals 0 to x equals 1 of x to the 1/4 plus 1 squared minus x to the 4th plus 1 squared dx. This concludes our lesson on section 6.2, volumes of rotational solids revolved about a non-axis line.